Picture this. You've got a Dell Latitude 5420 motherboard on the bench. It's totally dead. You press the power button and you get absolutely nothing. No display, no fan spin, maybe just a blinking light if you're lucky. So where do you even begin to diagnose a modern, highly complex board like this? Well, welcome to This Explainer. Today, we're zeroing in on the silent, intelligent mastermind of the entire system, the PU601 controller. We're going to break down exactly what this chip does, how it thinks, and most importantly, how you can test it. Here is our game plan for today. We'll start with the Tiger Lake power problem, then meet the VR controller itself. After that, we'll run through the startup power sequence, SVID, and multi-phase power, and the power good signal. Finally, we'll wrap up with some practical no-display diagnosis. All right, section 1, the Tiger Lake power problem. Okay, let's dive right into this. Before we even touch a multimeter, we really need to understand why a complex multi-pin voltage controller is even necessary. Think about the power coming into the board. You've got massive, heavy-duty power from your 19-volt wall adapter or your battery. But on the other side of the equation, you have this incredibly delicate Tiger Lake CPU, which requires a highly precise, tiny voltage, usually anywhere from just 0.65 to 1.40 volts. You obviously can't just dump 19 volts directly into a delicate modern processor. It would literally go up in smoke in a millisecond. Safely bridging that massive power gap is exactly the high-stakes job PU601 has to handle. And here's the kicker. That CPU voltage, it's not just a single set-it-and-forget-it number. It dynamically shifts based on exactly what the laptop is doing at any given moment. In deep sleep, it barely sips power at about 0.65 volts. Idling, it bumps up to 0.75. Booting to the Windows desktop brings it up to 0.9 volts. But under a heavy turbo load, like launching a big piece of software, it spikes to between 1.1 and 1.4 volts. The CPU absolutely needs an intelligent controller to continuously adjust this voltage up and down in real time. Moving right along to section 2, meet the VR controller. So who actually manages this intense balancing act? Meet the ISL 95860 HTZ-T. If you're looking at the LAK491P schematic, you'll see this designated as PU601. This little chip is a multi-phase pulse-width modulation controller specifically designed for Intel IMVP platforms. Its ultimate job? Regulating the main CPU core voltage, which we call the plus VCIN rail. Think of this microchip as the ultimate gatekeeper for the whole system. If PU601 fails, your memory won't initialize, BIOS code won't execute, and you are for sure never getting a disk array. Let's zoom in a bit and look at the microscopic symphony that happens the exact moment PU601 wakes up. First up, its internal LDO starts, generating the chip's own internal power supplies. Once that's up and stable, the reference generator kicks in to create highly precise voltage references it uses for measuring. Finally, the PWM engine fires up. This engine generates switching pulses at mind-blowing speeds, 500 kHz, 800 kHz, sometimes even 1 MHz depending on the design. That means it is actively adjusting power up to 1,000,000 times a second. Section 3, the startup power sequence. Now, a controller this powerful doesn't just wake up whenever it feels like it. It's actually highly dependent on a very strict chronological sequence of prerequisite power rails. Basically, a bunch of stuff has to happen first. In Stage A, the 3.3-volt and 5-volt always-on rails have to exist. Then, Stage B, primary rails like 1.8-volt primary, 1.05-volt rails, and VCC INAX auxiliary activate. Stage C brings up the delicate memory rails. Only after all of those underlying dependencies are met, we hit Stage D, where the embedded controller finally sends the enable signal, IMVP VR on EN. If any of those earlier stages fail to show up, PU601 just stays asleep. All right, Section 4, SVD and multi-phase power. Assuming PU601 does get its wake-up call, how does it handle sudden demands for power? Well, it's all about communication. The Tiger Lake CPU and PU601 talk to each other over a digital bus called SVID, Serial Voltage Identification. You can picture it kind of like a rapid-fire conversation. The CPU shouts, "Hey, give me 0.72 volts," and PU601 instantly adjusts. A millisecond later, the CPU says, "Okay, now increase to 1.15 volts." PU601 complies immediately. This high-speed negotiation happens thousands of times a second to keep things perfectly stable. And when that CPU hits a heavy turbo load, it can demand 80 amps or more. Let that sink in for a second. 80 amps on a thin laptop motherboard. That is an absolutely massive amount of current. If you tried to shove that much power through a single MOSFET, it would instantly melt, and you'd have a very expensive paperweight on your hands. So to prevent a fiery death, PU601 uses what's called multi-phase operation. Instead of forcing all that current through one huge pipe, it's like splitting a massive physical load among a team of workers. By dividing an 80-amp load into, say, 4 separate 20-amp phases, the engineering benefits are huge. You get vastly lower heat spread out across the board, way better electrical efficiency, much less voltage ripple, and a significantly faster transient response to those rapid-fire SVID commands from the CPU. Section 5. The Power Good Signal. This brings us to the climax of the whole startup journey. It's the final, critical handshake. Step 1, the output voltage plus VCCIN successfully stabilizes. Step 2, PU601 proudly asserts the IM VPR_VRPG, or power good signal, basically saying, I did my job. Step 3, that signal translates into PCH PWOK. And finally, Step 4, the CPU and PCH receive this confirmation, which lets them continue booting and execute the BIOS. If this sequence fails, if PU601 never sends that power good signal, the entire platform just halts, dead in its tracks. But what happens if something actually does go sideways? Well, PU601 acts as the ultimate bodyguard with a bunch of internal protection systems. It monitors for overcurrent, quickly detecting if a CPU is shorted. It watches for overvoltage, like if 1.5 volts suddenly spikes to a dangerous 2 volts, it shuts it down. It monitors undervoltage, catching unexpected drops. And it even tracks overtemperature. If it detects any of these anomalies, it kills the power instantly to prevent catastrophic damage to your board. Finally, Section 6, Practical No Display Diagnosis. All right, we've covered the theory. Now let's translate that into actual bench work. When you're staring at a no-display board, checking plus VCIN is one of your absolute most vital steps. Here is the action plan. Grab your multimeter and set it to DC voltage. Find a solid ground somewhere on the motherboard and place your black probe there. Then take your red probe and touch it directly to the largest CPU core coil right next to the VRM. Now, check out your meter. What is the board trying to tell you? If you measure 0 volts, the VR isn't starting at all. If you get a short or extremely low resistance to ground, you might be looking at a dead CPU. If you measure a nice, stable voltage somewhere between 0.7 and 1.5 volts, awesome, the CPU VR is running normally. But if you see the voltage pulsing up and down, that means the startup sequence is failing midway, or PU601 is hitting one of those internal protections we just talked about and continuously resetting. Based on that one single measurement, your diagnostic path splits entirely. If you have no VCCIN, you need to work backward. Check the 19-volt input to PU601, see if the EC is sending that enable signal, check for coil shorts, and test the enable circuit. On the flip side, if VCCIN is present and totally stable, stop testing PU601. Your problem is downstream. You need to check if the power good signal is actually leaving the chip, verify PCH power OK, look for BIOS activity, check memory rails, and investigate the EDP sequence to the screen. So, we've fully decoded the PU601 controller. You now know how it wakes up, how it negotiates power, and how it acts as a bodyguard for the Tiger Lake CPU. Now, the rest is up to you. Get your multimeter ready, hook up your power supply, and ask yourself, what voltage are you actually measuring on that core coil? And what is your power supply's current consumption during the startup sequence? Let the numbers tell you the story. Happy diagnosing.